Imagine I give you these 5 numbers 5, 2, 8, 1 and 3 and I ask you to arrange them from smallest to largest. Of course, you could look at all the numbers and manually arrange them. But how would a computer do it? More importantly, how can we write a program that takes an unsorted array and automatically puts all the elements in the correct order? That's exactly what sorting algorithms help us do. And in today's video, we are going to understand one of the simplest sorting algorithm, bubble sort. Don't worry if you have never studied sorting algorithms before. We are going to understand bubble sort visually, step by step, with a complete dry run, and finally we will implement it. Before understanding bubble sort, let's first understand what sorting actually means. Sorting simply means arranging data in a particular order. For example, suppose we have 5, 2, 8, 1, 3. If I arrange these numbers from smallest to largest, I get 1, 2, 3, 5, 8. That is ascending order. We can also arrange them from largest to smallest, 8, 5, 3, 2, 1. That will be descending order. So, whenever we talk about a sorting algorithm, the basic goal is very simple. Take an unsorted collection of elements and rearrange those elements into the required order. In this video, we will focus on ascending order. You might be wondering, why do we even need sorting? Imagine you have thousands of student marks. Without sorting, it can be difficult to quickly understand who scored the highest marks, who scored the lowest, or how students are ranked. Or imagine an e-commerce website. Products may need to be sorted by price, rating, popularity, or review count. Sorting is also useful in searching algorithms. In our previous video, we discussed binary search. Remember one important condition for binary search: the data must be sorted. So, sorting is not just an isolated topic. It becomes a building block for many other algorithms and real world applications. Let's take a very small example because I want you to understand exactly what the algorithm is doing. Our array is 52813 and our goal is to get 12358. Now here is the important question. How can we transform the first array into the second one? Bubble sort uses a very simple idea. It repeatedly compares two neighboring elements. If they are in the wrong order, we swap them. That's the entire basic idea. But let's not jump to the code yet. Let's understand exactly what happens. There is one word you need to understand before we continue: adjacent. Adjacent simply means elements that are next to each other. In this array, 52813, 5 and 2 are adjacent, 2 and 8 are adjacent, 8 and 1 are adjacent, and 1 and 3 are adjacent. Bubble sort looks at these neighboring pairs one at a time, so it doesn't randomly compare any two elements. It follows a specific pattern. First pair, then the next pair, then the next pair, and so on. Now we have the most important rule of bubble sort. Whenever we look at two adjacent elements, we compare them. Suppose we are sorting in ascending order. If the left element is greater than the right element, they are in the wrong order. So we swap them. For example, 5 and 2. 5 is greater than 2. So 5, 2 becomes 2 and 5 after swapping. But suppose we compare 2 and 8. 2 is already smaller than 8. So they are already in the correct order. We don't swap them. This simple comparison and swap operation is what bubble sort repeatedly performs. Let's start our actual dry run. Our array is 52813. We begin with the first two elements, 5 and 2. We ask, is 5 greater than 2? Yes. And because we are sorting in ascending order, this means they are in the wrong order. So we swap them. Now the before array was 52813. After the swap, 25813 is our new array. Notice here, we haven't sorted the entire array yet. We have only fixed the first pair, 2 and 5. Now we move one position forward and compare the next adjacent pair. Now we compare the next pair, 5 and 8. Is 5 greater than 8? No. 5 is already smaller than 8. So they are already in the correct order. We don't swap them. The array remains 25813. And now we move forward again. This is important to understand. Bubble sort doesn't restart from the beginning after every comparison. It keeps moving through the array and comparing neighboring elements. Now we compare 8 and 1. Is 8 greater than 1? Yes. So they are in the wrong order. We swap them. The array becomes 2, 5, 1, 8, 3. Again, notice that we are only changing these two neighboring elements. Now we move to the final pair in this pass. Now our final comparison for this pass is 8 and 3. 8 is greater than 3, so we swap them. Our array becomes 2, 5, 1, 3, 8. And now something very interesting has happened. Look at the last element. We have 8. It's the largest element in the array. And after moving through the array, the largest element has reached the end. This is where the name bubble sort starts to make sense. The larger element gradually moves towards the end, almost like a bubble rising to the surface. That's why we call it bubble sort. Let's stop here and understand what one complete pass achieved. We started with 5, 2, 8, 1, 3. After comparing all adjacent pairs, we got 2, 5, 1, 3, 8. The entire array is not sorted yet, but we know something important. The largest element 8 is now in its correct position. We don't need to move 8 anymore. So during the next pass, we can focus only on the remaining elements. This is one of the key ideas behind bubble sort. Now we start our second pass. Our current array is 2, 5, 1, 3, 8. Remember, 8 is already fixed, so we don't need to compare it again. First, compare 2 and 5. 2 is smaller than 5, so no swap. Next, compare 5 and 1. 5 is greater than 1, so we swap them. The array becomes 2, 1, 5, 3, 8. Next, compare 5 and 3. Again 5 is greater than 3, so we swap. Now we have 2, 1, 3, 5, 8. And again the largest remaining unsorted element 5 has moved into its correct position. Now let's perform the third pass. Our array is 2, 1, 3, 5, 8. Compare 2 and 1. 2 is greater than 1, so we swap them. We get 1, 2, 3, 5, 8. Now compare 2 and 3. 2 is smaller than 3, so we don't swap. At this point, the remaining elements are already sorted. We could continue checking, but we don't need to make any changes. And finally, our array is 1, 2, 3, 5, 8. We started with 5, 2, 8, 1, 3, and bubble sort gradually moved the larger element towards the end. The important thing is not just memorizing the final result. You should understand the process. Compare adjacent elements. If they are in the wrong order, swap them. Continue moving through the array. After one complete pass, the largest remaining element reaches the end. Then repeat the process for the remaining unsorted portion. Now you might ask, why do we need multiple passes? Why can't we just go through the array once? Now because one pass doesn't necessarily put every element in its final position. For example, after our first pass, 2, 5, 1, 3, 8, we know 8 is correctly positioned, but 2, 5, 1, 3 are still not sorted. So we need another pass. The second pass fixes the next largest element, which is 5. Then another pass fixes the next one. So each pass places at least one large element into its final position. That's why bubble sort repeats the process for all array elements. This visual makes the idea much easier to remember. After pass 1, we have 2, 5, 1, 3, 8. The 8 is fixed. After pass 2, we have 2, 1, 3, 5, 8. Now both 5 and 8 are fixed. After pass 3, we have 1, 2, 3, 5, 8. Now the array is sorted. So we can think of bubble sort as gradually creating a sorted section on the right side. After every pass, that sorted section becomes larger. Now that we have completed the dry run, let's summarize the algorithm. Step 1, start from the first element. Step 2, compare it with the next element. Step 3, if the left element is greater than the right element, swap them. Step 4, move to the next pair and repeat. Continue until you reach the end. At this point, the largest unsorted element will be at the end. Then start another pass. But this time we don't need to include the elements that are already sorted at the end. Keep repeating until the array becomes sorted. Now let's convert our logic into Java. You can use any other language. The first thing we need is an outer loop. Why? Because we need multiple passes. So we can write for int I equals 0, I is less than array length minus 1. Then I plus plus. Think of this outer loop as saying perform another pass through the array. For an array containing 5 elements, we may need up to 4 passes. So this outer loop controls how many times we repeat the process. Inside the outer loop, we need another loop. This inner loop performs the actual comparisons. We compare array of j with array of j plus 1. Why j plus 1? Because we want to compare adjacent elements. For example, if j points to index 0, we are comparing array of 0 with array of 1. Then j becomes 1. We are comparing array of 1 with array of 2. Then array of 2 with array of 3. And so on. Now notice something important here. We are using array dot length minus 1 minus I. Why subtract it? Because after every pass, one more element is already fixed at the end. There is no need to compare that sorted portion again. Now we reach the most important part, the swap. We first check is array of j greater than array of j plus 1. If yes, they are in the wrong order. Suppose we have 5 and 2. We want 2 and 5. But we cannot simply write array of j equal to array of j plus 1 because then we would lose the original value 5. So we temporarily store the first value. We do temp equal to array of j. Now temp contains 5. Then array of j equal to array of j plus 1. So array of j becomes 2. Finally, array of j plus 1 equal to temp. Now array of j plus 1 becomes 5. The two elements have successfully swapped. This temporary variable is a very common technique when swapping two values. Now let's put everything together. The outer loop controls the passes, the inner loop compares adjacent elements, the if condition checks whether they are in the wrong order, and the temporary variable performs the swap. So the entire bubble sort algorithm is basically these three ideas. Pass through the array, compare neighboring elements, swap when they are in the wrong order. Once you understand these three ideas, the code becomes much easier to remember. Don't try to memorize the code first. Understand the process first and then the code will make sense. Let's connect everything we learned with our original example. We started with 52813. Pass 1. 5 is greater than 2, so swap. Then 5 and 8, no swap. 8 and 1, swap. 8 and 3, swap. The final array after first pass is 25138. Now 8 is fixed. Pass 2. 2 and 5 no swap because they are in correct order. 5 and 1 swap. 5 and 3 swap. We get 21358. And now 5 and 8 are fixed. Pass 3, 2 and 1 swap. 2 and 3 no swap. And we get 12358. Now the array is sorted. This is exactly what our code is doing behind the scenes. Now let's talk about performance. Bubble sort is easy to understand, but it is not considered an efficient sorting algorithm for large data sets. In the average and worst cases, its time complexity is O of n squared. Why? Because we have one loop inside another loop. The outer loop performs multiple passes, and during each pass, the inner loop performs multiple comparisons. So if the number of elements increase significantly, the number of operations increases very quickly. There is an optimized version of bubble sort where we can stop early if an entire pass makes no swaps. In that case, if the array is already sorted, the best case can become O of n. We will see that optimization shortly. There is a small but useful optimization we can add. Imagine our array is already sorted 1, 2, 3, 5, 8. During a complete pass, we compare every adjacent pair, but not a single swap happens. That tells us something important. If we went through the entire unsorted portion and didn't make even one swap, the array is already sorted. So there is no reason to continue with more passes. We can use a Boolean variable called swapped. Initially, swapped equals false. Whenever we perform a swap, we change it to true. After the pass, if swapped is still false, we break out of the loop. This optimization avoids unnecessary work for already sorted or nearly sorted arrays. Now let's look at space complexity. Bubble sort works directly on the original array. We are not creating another array containing all the elements. We use only a few extra variables such as I, j, temp and optionally swapped. The number of these variables doesn't grow with the size of the input. Therefore, the extra space complexity is O of 1. This is called constant space. Here is a common interview or conceptual question: why is it called bubble sort? The reason is the way larger elements move toward the end of the array. Remember our example, the value 8 started here, 52813 was our array. During the comparisons, 8 moves past 1, then it moves past 3. Eventually, it reaches the last position. So the larger elements appear to bubble toward the end. That's where the name bubble sort comes from. If you remember only one thing from this video, remember this: compare, swap, move, repeat. Compare two adjacent elements. If they are in the wrong order, swap them. Move to the next pair. Repeat this process across the array. After one complete pass, the largest remaining element reaches the end. Then start another pass. Once you understand this mental model, the Java implementation or implementation in any other language becomes much easier. In next episode, we are going to learn another sorting algorithm, selection sort. And selection sort works very differently from bubble sort. Instead of repeatedly swapping neighboring elements, we will search for the smallest element and place it in its correct position. For example, if our array is 52813, selection sort first looks for the smallest element, that's 1. Then it places 1 at the beginning. Then it looks for the smallest element in the remaining portion. We will go through the entire process with a detailed try run and implementation. If you are following this algorithm series, make sure you continue with the next episode. Thank you for watching. I'll see you in next episode.